All right, let us get started. I want to review this worksheet because I want us to be very comfortable with the Lewis structures so we can come back later and do the VSEPR structures. The next ones, remember that I know I say number of electrons here, but what I mean is number of valence electrons. Boron is the exception to the rule. So boron and beryllium, hydrogen, helium, they are okay not having a full octet. So boron, does anyone know how many valence electrons boron has? 3. So boron, so we have 1 times 3 plus, what is the valence electrons of iodine? Yeah, 7. So that should be 24. So this one should look like this. B. And each of these iodines should have 6 lone pairs. So 2, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So yes, this boron here does not have a full octet, so I don't have to move any electrons around because boron is very happy having just 6 in its outer. So this one is a unique and rare one, but this is the Lewis dot structure for boron. We did the rest of the first page on Friday. So let's finish the rest of them real quick. H2O, the valence electrons of each of those hydrogen will be 1. So that's 2 times 1 plus 1 times 6. That's the valence electrons of oxygen. So 8. So yeah, so oxygen will have hydrogen. And because we can't get any more lone pairs onto these hydrogens, we're going to have to put them around the oxygen. So that's 2, 4, 6, 8. So that would be the Lewis dot structure for H2O. Okay. PCl5, so phosphorus is 5. And then each of those chlorines is 7. That's 35. I guess that's 40. Correct me if I'm wrong. All right. I do not like doing math in my head. So P, and then you'll just do 5 CLs around this one. So CL, 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 CL. So that's already 10. So 2, 4, 6, 8, 10. And then we'll just put those lone pairs. Two, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. So we are done, and that would be the Lewis dot structures for phosphorus. Just remember, sorry, PCl5. Just remember that if you would prefer to put lone pairs instead of double bonds here, you are also correct. So I just prefer to do the bonding just because it prevents me from having too many confusing dots, but both are going to be correct. Okay. Next will be SF4. So sulfur is 6. So that's 1 times 6 plus 4 times 7. That's 28 plus 6 would be 34. Wait. Yeah, okay, thank you. 34. So sulfur in the middle, because it's less electronegative than the fluorines. So F, 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 F. So then I'll put in those lone pairs. Let me count them. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So we're missing 2 lone pairs, and we only, if you ever have an extra set of lone pairs you need to add, always add them to the center element or atom. Okay. ClF3, so that's 1 times 7 plus 3 times 7, so 21 plus 7 is 28. Cl will be your central one because it's not as electronegative as fluorine. All right, 2, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So this one's missing 4 lone pairs. So I need to put both of those lone pairs on the chlorine. We don't put them on the external ones, only the center. All right, let's keep chugging along. XeF2. So this is a noble gas and it has 8 valence electrons. So 1 times 8 plus 2 times 7. So that's 14 plus 8, which would be 22. So Xe will be in the middle because it's less electronegative than fluorine. So I'll do F, F. 2, 4, 6, 8, 10, 12, 14, 16. So this one's missing more than just 4. So 16, wait, 2, 4, 6, 8, 10, 12, 14, 16, yeah. 18, 20, 22. So yes, this one has a lot of lone pairs, but they all have to go on the center atom. Okay. And then we already did SF6, so I'll just do that one real quick. So S, my numbers, yeah. So I think this is 48. That's 1 times 6 plus 6 times 7, 48. But yeah, we did this last class. All right, next will be BrF5. Bromine is 7. And then fluorine is also 7. So that's 35 plus 7 should be 42. So I'll just do bromine in the middle. And then put those 5, 2, 3, 4, 5. 2, 4, 6, 8. That should be 16, 24, 26, 28, 30, 32, 34, 36, 38, 40. That means that the last 2 need to go on the bromine. And then the last one is XeF4. So that's 4 times 7, that's 28. Plus 8 would be 36. 2, 4, so that's 8, 16, 24, 32. So you need to add the extra 4 onto the center atom. The key is up. I'm just kind of like just went quickly through it. Same thing as the key. Let me know if anything is confusing so we can go through a little bit more depth because we're going to move on to Vesper. Right. Any questions? Okay.
We have our exam next Monday, right?
Yes, 1 week from today. So I would honestly, if I was in your shoes, take the opportunity this week to get caught up on everything. So this weekend, which I'm sorry that you're going to study over the weekend, you can focus on the stuff for the exam. We're going to have some review on Friday, but it'd be wonderful if all of the homeworks were done. Still have one more homework I need to put up, but all the other homeworks could get done. The quizzes, because we have 2 quizzes out right now, just to make your lives a little bit easier. And then once you finish the homework and quizzes, you won't have another quiz ever again for this class. Like this is, you're done once you finish your homeworks. Because after the third exam, there's no more deadlines.
The third exam, we have just the final.
So I have the third exam on Monday, and then we're gonna come back on Wednesday for a review session for the final.
Yeah.
And the final will be on Friday. We're pretty much done. Looks like my screen is frozen. Why can't I click on it? All right, I'm just gonna refresh this. Anyway, it's not working. But I don't need it. There it goes. Okay, so Vesper and Lewis structures are in the same boat. You have to be comfortable with Lewis structures to be successful with VESPR. So Vesper stands for valence, shell, electron, I think it's full repulsion. I need to double check that P. But it's all about shapes. So just like what we did with Lewis structures, we were creating shapes with how our molecule should look. Vesper is the same way, but we're kind of connecting the dots from electron configuration. And electron configuration, I talked about how those shells look, how the S is like a little small circle, the P looks like a dumbbell, the D looks like double dumbbells. So it's all about estimating where those electrons are. So we're not going to get into the nitty gritty that you might see in general chemistry, but it is relevant to the shapes of these molecules. So when we create a molecule, the first thing I want to point out is you have all of this space around a central atom. And if I was to add hydrogens onto the central atom, those hydrogens are not going to be right next to each other. They're going to try to space themselves out and spread themselves out to be on the opposite sides from each other. If I start adding more hydrogens onto it, same concept. They're just going to try to fill the space around the center atom as completely as possible, try to get equal distance from each other. So they're not on top of each other. So that's because electrons are all negatively charged. And the more electrons you have on there at the same charge, they're going to repel each other. So they're going to try to fill the space and they repulse each other.
That's why you won't see two things, next to each other on top of each other. So that's what VSEPR is all about, is using the electron cloud around it to estimate each shape. And eventually we're going to be using this document. So if you have this ready to go, I'm going to have a PhET simulation and we are going to go through this together and get this answered. And then we're going to do this worksheet, the second half of this worksheet. So let's talk VSEPR. Our objectives for this section are to define the electron domains. That's the cloud around the central atom and trying to, configure the shape. To count the electron domains around an atom in a Lewis dot structure, to identify the VSEPR shapes up to 4 electron domains and 2 lone pairs, and to use the ideas of VSEPR to predict the electron and molecule geometry around an atom in a Lewis dot structure. So here's just an example of those electron clouds. In this class, we're going to deal with relatively smaller molecules like CO2, CH4. But as you get further on in chemistry, the topics we cover now are still relevant. So these are larger molecules that are more extensive, but you can see how they still have a shape to them based on the electron cloud and where the electrons are. So it is very relevant to, trying to fill the space around a central molecule where those electrons will be. So this is a great example of like how that shape is still helping and shaping things. So previously we talked about the Lewis structures and we tend to draw them in 2D, like flat on a page. But when you're trying to fill the space around a central atom, you have like a giant circular orb. So it's 3D. So going from Lewis structures, we need to be comfortable creating those Lewis structures in 2D to then be able to visualize things in 3D. That's the VSEPR. In Lewis structures, we also kind of create the connection of the atoms. So are they bonded? Are there lone pairs? And then in VSEPR, it's all about the shape of the molecule. So you need to have one to do the other, but they are slightly different. Here, if I just look at this drawing and I had it flat in front of you, the way that it's drawn, it would go from like my hand right here to being flat. But that's not going to happen because what is the bond? Can anyone tell me if this was a flat, what would be the bond angle here? Is that a right angle? What angle do you think that is? Do you remember the degrees? 90, right? But in here, if I was to evenly space it, let's say I have around it like 360. Yes, if I divided 360 by 4, it would give me 90. But you're not on a 2D plane, you're on a 3D plane. So the way that this works is if you were to divide it by all directions, it would even out to be 109.5 degrees. So it's not just flat, it's on a 3D plane. So we have these little dashes and I forget what the other one. Wedges, yeah, dashes and wedges. So this wedge means it's coming out in front of you, towards you, and then dash is going behind it, or vice versa. It doesn't matter. One's coming at you, one's going away from you. So it's not flat down like on the page. So Lewis, it doesn't matter with Lewis being accurate with those bond angles, but with VSEPR, it starts coming into account. So why is a 3D shape important? It's connected to so many aspects of chemistry, spectroscopy, reactivity. That's just more of the big picture things, but being able to visualize and figure out, how are things attaching to each other, that's all 3D shapes. So there's a lot of relevance, even if we're not getting into it in this subject, I guess in 1320. So electron domains, that's the main part of VSEPR. So it's the electron cloud around the central atom where the electrons, so clouds are clusters of charge on the central atom. So remember, charge is going to be those negative electrons. So where are they going? One domain can be any of the following: an unpaired single electron, a lone pair, a single, double, or triple bond. So it's pretty much counting all the things attached to a central atom. It could be one electron or 2 electrons or a variety of different bonds. So that's where things are connecting. So valence shell electron, oh, that's the P, pair. So she's just replacing with domain. But yeah, pair is that P, repulsion theory. So the domains are negatively charged because they are filled with electrons. Electrons are negatively charged. These domains repel each other because like charges will repel each other, just like if you had magnets, the two negative sides of the magnets will repel each other. So if you have a bunch of negativity, they're going to repel each other until there's nowhere else for them to go. These domains will spread out as far from one another as possible until they fill the shell. So the procedure is when you're trying to estimate what is the shape of this compound, you start with the Lewis structure and then let the domains repel each other in 3D to generate a VSEPR structure. And I'll show you how to do that. Start, if you have your computer with you, is having the SPET molecular shapes tool. If you don't want to do it with me, you're welcome to do this later because I'll do it up here with you. But if you can have this with you, we can answer this worksheet as we go through it. So I'm going to switch to this SPET molecule. I love SPET simulations. You already know that. They're a lot of fun. And if you're a visual learner, like myself, when I was learning this, my professor would come to class with all of these models and she would do it right in front of you. But I think this is a better way of doing it just because you can do it from home. So when we have a compound, let's say this is like CO2 or even anything like CS2, things like that. So you have a central atom, we don't know what it is, and then it's connected to two of the same elements. The furthest two things can get away from each other is going to be 180 degrees. That's the maximum they can repel each other. Because if they started going near each other like this, you can see how those electrons are trying to get away from each other. They're trying to fill that shell. So if I was to show the bond angles, this is the maximum they can get. Always going to get back to 180. If I was to add more things to this central atom, the bond angle will change. But if you were to have just something like this, that's the best you can get. If you look here, let me see this linear lone pair angle. Okay, so on this worksheet where it says angle, you can write down the angle. So I guess go ahead under angle, write down 180. And then I'm not sure what handwritten would be, but I would definitely say maybe draw it out. Yeah. So I do want to point out that you have a central atom here, and if you need to count the things attached to the same central atom, if you count, one molecule here, one molecule here, and that's why you see on the left-hand side it says number of electron domains. It has a 2. That's what it is. If I was to remove one of those bonds and replace it with a lone pair, that's what I did here. I took one off, added a lone pair. It would still be 180 degrees from the central atom here, because that's the furthest it could go out. So you can also draw under one lone pair. This, it is possible. It's pretty rare, but it is possible if you want to draw this out. It's still 180 degrees. I could also take this out and put 2 lone pairs, but I think that's very unheard of. Because then it wouldn't be a full, unless this was like beryllium.
That was asking for on the worksheet.
I think so. I didn't check the key. I can take a look at the key. I've seen a bunch of these fun little worksheets. Maybe I'll get another one out next time. Okay, now let's think about what shape this is. Let me go back. What shape do you think this is? Don't be right, but like, what does it look like to you? Like a Q-tip, that's good. So it's a straight line. So if I was to click down here for the electron geometry, The electron geometry is how many things are attached. So if it's only two things attached, it's always going to be linear. So yeah, like a Q-tip, very straight line. Molecular geometry will change if I start to take these off and replace them with lone pairs. But in this case, if there's always two, it's going to be linear. So if you see in the first column or underneath all of these, you can see the shape names. Yeah, let's keep playing around. Let's remove this and add 3 bonds to it. So under angle, you can put the degrees. So if I have 3, the maximum distance they can go from each other is 120. If they even were to start using the 3D plane, it'll still always max out at 120 degrees. So yes, it is 2D for anything with 3 on them, but this is the best we can go. And the shape is called trigonal planar. But notice if I start trying to like make one move closer to each other, the other ones are gonna rearrange to try to get as far as they can. Sorry, I'm gonna get up that key real quick. Nope, there is no key. So yeah, we'll just do our best to make our own key. All right, so trigonal planar. If I was to remove one of these bonds and replace it with a lone pair, so lone pairs are pretty electronegative, and sometimes they can put a little additional push because they're a different shape, but it will still be 120 degrees here. So that's why we'll put 120 under angle. For the handwritten, you just want to write it your own way. Like, you're pretty much going to replicate what you see here in your own handwriting. Let me see if I can take off. Yeah, and if something similar if you were to have 2. So if I take off 1, it's now bent. You can see. So it's still going to be the electron geometry because you have 3 things attached. It's still going to be trigonal planar because that's always the amount of things attached. If there's 2 things attached, it will always be linear. If there are 3 things attached, whether it be a bond or a lone pair, it's always going to be trigonal planar, but the molecule geometry starts adjusting when the shapes start changing. So electron pairs aren't really existing in space. They do have place, but they're not like replicated by a different like element. So they're going to be a little bit different. So it does affect the overall shape. So that's why this one's going to be bent because you can see, take away the bond, it's just going to be a bent shape. So yeah, once again, lone pair, it does take up space, but you're not going to see it like you would see a bonded element. That's why it changes this. Let me take this off and I'll add 4 things to this. So the second I started adding 4, you can see how it's no longer going to be 2D because it has to maximize the 3D around the structure. So the best way we could do that is going into, you have one coming at you like this, one going away from you, and the rest are going to be in 2D, but they're all 109.5 degrees. And if you have 4 things attached, the terminology is tetrahedral. So 4 tetrahedral. If I remove one of those bonds and replace it with a lone pair, it's still going to be 4 things attached to it. So the electron geometry is tetrahedral, but remember, like, this is kind of invisible. So you can see, like, it looks kind of like a pyramid. There's 3 here, so that's why this is going to be called pyramidal or pyramidal. Pyramidal, I like a little bit better, but it looks like a pyramid. That's why they call it this. That's just the shape of this with those 3 bonds. If I remove one more bond and add a lone pair, it's still tetrahedral electron geometry because 4 things are attached. But remember, these electrons are kind of invisible. You can still see this looks kind of bent. So this would be called bent if there were 2 lone pairs. All right, I'm gonna add 5 things. So that's 2, 3, 4, 5. What happens? So the way that the 5 works is you have this top and bottom, the maximum this top and bottom can give from each other is 180 degrees. But to fill the rest of it, you have this sideways. So you have your, one way and then the other way. So the best these can do is 90 degrees from each other. But from this direction, they can be 120 degrees from each other. So if you have a very large something that needs to be further away from each other, they can always pick and choose to be one of these 120s. But you still have 90 degrees. So 90 from the top and the bottom, and then from, if I was to do it this direction, 120 from the sides. So if you have 5 things attached, it's called trigonal bipyramidal or bipyramidal. And then you could still start replacing them with lone pairs. Lone pairs are very electronegative. So they're going to go somewhere very specific. I'm going to take one off and I'm going to put one on. So a lone pair is not going to go into one where you have to have the 90 degrees. They're going to go into the one where we have 120 because they're so electronegative and they're going to want to be as far away from everything as possible. So this one is fun because it looks like it's a seesaw. But once you have one lone pair, so it's kind of like seesawing back and forth. So you have, this is what's on the playground holding the seesaw together, and then you have this and this. But the lone pair will go somewhere very specific. If I take off another bond, where do you think the lone pair will go? It'll be on the 120 plane, not the 90 plane. So I'll take off one and replace it with a lone pair. And you can see it's on the 120 plane. So the other 3 will be 90 degrees from each other. And this is what we call a T-shaped molecule because it does make a T. So remember, those lone pairs are invisible if I was looking at the shape, not the cloud. This makes a T-shape where your bonds are 90 degrees from each other and the lone pairs are 120 degrees from each other. There is a case where I can have 3 lone pairs, which we already did on our Lewis dot structure. So I'll take that and add that on. And this is now back to being linear because the shape will be linear because the lone pairs will occupy the side that has the 120 degrees. So you can see these 2 bonds are 180, making this now linear. But if I was to ask you the electron geometry, it's still considered trigonal bipyramidal because there are 5 things attached to the center atom. So just double check before you answer a question. Is it asking electron geometry or is it asking the molecule geometry? Okay. All right. Let me take these off and now move on to the 6 range. So, under angle for the 5, you want to put 90 and 120. They'll have 2 different degrees for the 5. All right, for the 6, this one's easier because the maximum space all of them can be from each other is 90. So this one's a little bit easier because if I start removing things, those lone pairs will all go to the same spot, but they're all 90 degrees from each other. So under angle for that, you'll put 90. But we can actually put a bunch of lone pairs on this and take off bonds. So I'll do that now. If I take off one, it also looks like a pyramid, but it's a square pyramid because there's 4 things. So if I was to make it look like a pyramid, the lone pair would go to the bottom and it looks kind of like a pyramid. But everything else will always be 90 degrees from each other. Let me take off another one. So here's another one. If I was to take a lone pair off, just know these lone pairs want to be as far away from each other as possible. It's not going to go next to it. So it's not going to go to one of these bonds right next to it. It'll go as far away, which means it'll go here. So I'll remove one bond and add a lone pair. So that's the furthest these lone pairs can get from one another. And that means we now have pretty much a square planar molecule. So it's still octahedral, so that's the word, sorry. If there are 6 things attached, it's octahedral, but in this case with 2 lone pairs, it's now square planar. when you get past here, there's only one place a lone pair can be. So that was a little bit easier to decide. They have to be right next to each other. And we go into being back to T-shaped because it does make a T because the lone pairs are occupying the other ones. It's still 90 degrees. And then there's one more I can do. I can take one more off and I can add a fourth one. So now we go back to being linear. So my advice, let me go to the real molecules. We might have some of these real molecules. Yeah. Okay. So let's do these together because some of these are going to be on our worksheet. Okay. On page 2 of our worksheet, we have water. Here is what water looks like. Question number 1. What is the electron geometry of water? Meaning how many things are attached and what word belongs to that?
Like where?
So the electron geometry is how many attachments are there. So if I was to show you water, how many things are attached to it? 4. So the electron geometry is tetrahedral, but the molecular geometry is different because we don't really think about these lone pairs. So like pretend these lone pairs are invisible. What shape do you see here? Bent. So for the VSEPR structures, I know my worksheet's not complete, but you can put electron geometry is tetrahedral, molecular geometry is bent under the VSEPR structure of water.
Go back to the first worksheet.
Yes, so that would be right here. You put tetrahedral and bent.
That's all we're looking for. We don't have to draw.
You can draw it if you want. I think on my key that I posted today, like I have it drawn out with the dashes and the wedges, but you don't have to do that. I think right now I want to practice naming it, so you can just put names. So these are the names we want. Let's see what else they have. Oh, they have CO2. This is CO2. So CO2 has 2 things attached, and that one's probably the simplest one because if there are 2 things attached, it's always going to be linear. If there's 1 thing attached, it's also linear, just so you know. But if there's 2 things attached, it is linear. But because there's no lone pairs on the central atom, both the electron geometry and molecule geometry will be the same number or same answer. So both will be linear. So for CO2 on page 1, you will put linear and linear. Let's do SO2. We did not do the Lewis dot structure for SO2, so let's do that real quick. So in your notes, or I guess I could do it on the board behind me. SO2. So what is the valence electron? 6 valence electrons of O. So that will be 6 plus 6, 18. So what will be the center atom? Sulfur. And there will be oxygen and oxygen. So let's add electrons. 1, 2, 4, 5, 6. 6. 2, 4, 6, 8, 10, 12, 14, 16. I still need 2 more, but I can start trying to add more to the center. But I think I also need to do 2 things here. Look at the sulfur. Is it full? Is it happy? No. So I'm going to add the extra valence electrons here, but I need to add one of these lone pairs onto the center because that would be
You just have to make one of them a double bond.
I need to double check, so we're gonna do this and then we're gonna do that. I think it might have two double bonds, but I need to have double check, so it'll be one double bond. 2, 4, 6, 8, 10, 12, 14, 16, 18. So the sulfur here, 2, 4, 6, 8 does have a full octet. 2, 4, 6, 8 has a full octet. 2, 4, 6, 8 does have a full octet. So the way this is drawn, it looks a little unique, but as of right now, this does have a full octet. How many things are attached to it? So you have this attachment, that lone pair counts as an attachment, and you have this attachment. So how many things are attached? 3. So the molecular geometry, let me make sure I'm right. I'm pretty sure I'm right,
That
but,
would be
okay. Yeah. It would be trigonal planar. Okay. So in this case, because this goes into more Jim one, because oxygen will prefer to be neutrally charged. I'm not gonna go into that now, this is Gen Chem. We're just gonna replace it with this, but 3 things, trigonal planar, but the lone pair is not counting towards the molecule geometry. So what shape is it? Okay, so electron geometry, it's gonna be 3 things, trigonal planar. Molecule geometry will be bent. So let's check. Good job. This is so much fun. Sorry, I don't sound like I'm having a lot of fun, but I am. Let's do XEF2 because I'm pretty sure we did that one on page 2. Okay. So let's do that one, XEF2. So in that one, if you were to look at your page 2, yeah, no, yeah, top of page 2, yeah, no, top of page 3. So XEF 2, it has 3 lone pairs to them, and just remember when they have 5 things attached, those lone pairs are going to go towards where there's the 120 degrees between them, because they want to be as far apart as possible. So 5 things attached. What is the electron geometry? No worries, it's complicated. Yeah, bipyramidal. Trigonal bipyramidal, because there are 5 things attached. So on your worksheet, you will put electron geometry, trigonal bipyramidal. But the lone pairs don't contribute to the molecule geometry. So let's focus just on the bond to it. So ignore the lone pairs. What shape does that look like? It's linear. So trigonal bipyramidal is the electron geometry. And the molecule geometry will be linear. BF3. So let's do BF3 and pretend it's BI3. Because F and I are all column, halogens. It'll be the exact same thing. So just pretend this is BI3. So this is on page 1. And here is BI3. How many things are attached to the central atom? 3. So what is the electron geometry? Okay. Are there lone pairs? Not the central atom. So they will have the same name, trigonal planar. Right. Oh, I think we did CLF3. Yeah. So bottom of page 2 is CLF3. So we did the Lewis dot structure and we found that there are 2 sets of lone pairs on the central atom. So how many things are attached to the central atom? 5. Lone pairs each count as 1, 2, 1, 2, 3, 4, 5. This electron geometry will be no worries, trigonal bipyramidal. But we do not count the two lone pairs in the shape. So what shape do you think it makes? T-shaped, yes. NH3, that's gonna be on page 1. Okay. So NH3, how many things are attached to the central atom? 4. So what will be the electron geometry? Tetrahedral. But the lone pair is not counted. So look at what it's doing if I was to ignore the lone pair. This could not be trigonal planar because it's not in plane with each other. It's not in like a 2D shape. Instead, it looks more like a pyramid, right? So what shape do you think it is? Trigonal pyramidal. So for me, when I was in y'all's shoes, I would always kind of mess this up and think it was trigonal planar, but that planar means it's in 2D flat, but the pyramid is for when like it's a little bit of pushing. That lone pair is pushing them away from each other. So this is trigonal pyramidal. Oh, CH4, also on page 1. Okay. So this is CH4. How many things attached? So what is the electron geometry? Tetrahedral. And what is the molecule geometry? Yes, no lone pairs, easy peasy, same thing as electron geometry, all tetrahedral. So I think we finished page 1. Good. What's after CH4? Oh yeah, SF4, we did that too. That's also on page 2. So SF4, we had a lone pair on that central sulfur. So just note that that lone pair will never go towards the 90 degree. It'll always try to get as far away as everything is possible, and it'll go to the 120. So there are 5 things attached to the center sulfur. So the electron geometry will be trigonal bipyramidal. You'll write that down as the electron geometry, but let's try to get that shape going. If I ignore the lone pair, what shape do you think this makes? Yeah, so this is like a seesaw if you were to be in the playground. So like this is attached to the ground and then this could go up and down, seesaw. Ooh, XEF4, that is on page 3, the last on page 3. Okay, so there are 6 things attached to this one. So 1, 2, 3, 4, 5, 6. This one, can anyone pronounce the name for the electron geometry? Octahedral. I know it's weird because octa makes me think 8. I know, but octahedral will be the electron geometry. If we were to ignore the 2 lone pairs, look at the way this is working. It's flat, right? So like it's kind of flattened out and there's 4 of them. So what shape do you think this is? Yes, it's not trigonal planar just because there's 4, not 3, but it's the same concept. It's flat and there are 4, so square planar. BRF5. Oh, let's finish. We're almost done and then we'll take a break. Okay. So BRF5, I think we also did that. Yeah, on page 2 or page 3. Okay. So BRF5, how many things are attached? 6. So it's octahedral. But what is this shape? Let me fix this. Make it look like it. Yeah, it looks like a pyramid. So this would be a square pyramidal. Perfect.
Next will be on page 2, PCL5. So PCL5, how many things are attached? 5. So electron geometry. Molecule geometry. Same thing. Okay, one more left. And that's gonna be SF6. Okay. How many things? 6. So electron geometry. Molecule geometry. Yeah. These are really fun to play around with. I think when I was in graduate school, I found something where like you could do a quiz or test on it. So I'm gonna go look for it during our break. But let me see if I can get that up and we can continue to quiz ourselves on it. But yeah, it is 12:52, so let's come back at 12:57. Recording in progress. Sorry. So if you were asked to do the orbitization of things, you want to count the things and also do it identified as an SP. That's if it's linear. If it's SP2, it would be trigonal planar. But don't be confused, because if it's like NH3, if you go back to your paper, and I want to do this with you real quick for your paper, for your worksheet. CO2 is linear. So maybe right here, we can identify, because it's linear, and if I was to say like what orbitization is around that center C, it only has 2 things attached to it. It's linear, so you will put SP. So you put SP either by the C, because I can also ask you about the oxygen, but I'm not. I'm going to focus on the center atom for all of them. So linear, 2 things attached, SP. So number 1, CO2 is SP. All right, number 2, Bi3, how many things attached? So if there are 3 things attached, and the good news here is if there was these lone pairs, or it doesn't matter, 3 things attached, SP2. That's the hybridization, that's the word. Hybridization around the center atom bromine. CH4. SP3, yeah, 4 things attached. Here's the trick one, NH3. It's SP3 because the lone pair counts as a thing. 4 things attached, SP3. I'm not counting bonds here. I'm counting attachments to the center atom. So NH3 will be SP3. All right, next page on page 2. H2O, trick one. What do you think? SP3, 4 things attached. See the trick. It gets us every time. 4 things attached, SP3. Those lone pairs count as 1 each. Okay. PCl5. SP3D. That's the hybridization of anything with 5. Which means that the next 2, they all have 5, right? They also will be SP3D. So SP3D, 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 now on page 6 or 3. SP3D because there's still 5 things attached. Now SF6. Yes, SP3D, D2, and that'll be the rest of them because the rest of them also have 6 attachments. So I could ask you anything. I can ask you about electron geometry, shape. I can also ask you about hybrid. So honestly, I know it's a lot to ask you to memorize, but the more you do it, and I'm going to do some examples in a little bit, the more it gets easier. So it's just telling you where are the electrons in the orbital. So
everything will have an S, everything will have a P, but it just depends on, you know, if they don't have a lot of, you know, things attached, it's just not gonna have very far orbitals, that's why it'll be SP or SP2. But as you start adding more and more attachments, there's running out of space, the electrons will be into different orbitals, and that's why you have to add the d orbital. So don't worry about the nitty-gritty details, just get comfortable recognizing 6 things this, you know, 2 things this. So let's get some practice in on the slides real quick. I'm gonna like change it up on the next slide because we've already done these. So I'm just gonna come up with some new things for us to do. And some practice and just go from, you know, how do we go from a Lewis dot structure to something else? Okay. I think we did previously the Lewis dot structure for formaldehyde, and that was kind of ignore this. It was CH2O. Let's practice doing the Lewis dot structure and trying to figure out everything we've learned so far. So if I was to ask you how to do VSEPR here, you always want to start with Lewis dot structure. That's going to be your first step. For you to be able to 3D model, you need to have it in a 2D model. So what's going to be step 1 doing the Lewis dot structure here? Yeah, C in the middle because it's written out front, but it's also the least electronegative, so it will be. But before I can do that, let's count the valence electrons. So carbon will have 4. Hydrogen will have 2 times 1. And then oxygen will have 6, right? So 4 plus 2 is 6, plus 6 is 12. So carbon will be in the middle. And then I will do hydrogen, hydrogen, oxygen. I can't put any lone pairs additionally on those hydrogen because hydrogen cannot have more than 2. So the only place I can put them is either on the carbon or the oxygen. So I'll start with the oxygen. So 2, 4, 6, 8, 10, 12. This has the correct number of lone pairs, but do you think it looks correct? So the way that I check is I'm like, okay, do each hydrogen have 2? If the answer is yes, and the hydrogens are happy. Oxygen, are there 8? Does it have a full octet? Yes, oxygen's happy. Does carbon have 8? No, carbon is not happy. So the only way to get carbon happy is to take 2 of those lone pairs and move them onto the bond to create a double bond. So that would be step 1. Step 1, get your valence electrons. Step 2, create your, I guess, skeleton. Step 3 would be to make sure everything is happy. Double check everything. So this one's not happy, so I'm going to move and make it a double bond. So double check, does everything have their full octets? The answer is yes. So now let's go to the next step. Let's apply VSEPR theory. How many things are attached to the central carbon? 3. What is the electron geometry? What is the molecular geometry? Same. There's no lone pairs on the central atom, so it will also be trigonal planar. So for molecular geometry and electron geometry, it is the same. Now let's apply this. What hybridization is happening on this formaldehyde? There are 3 things attached, so this is sp2.
The double bond doesn't make any change to the overall shape for geometry.
Nope. Yeah, it counts as one thing. Yeah, great question. Now, I'll give you a little looky into one of my quiz questions. All right, are you still taking notes of this? All right, I'm gonna erase this. Let's do a little quiz question. Because I don't want you to kind of look at this and think I'm trying to make your life harder. I'm not. All right, let's do BCl2H2. It's not always going to be so nice and everything's going to be the same element. So first things first, what do I do to create a Lewis dot structure? Count the valence. So carbon is 4. Chlorine is 7. Hydrogen is 1. Four plus 14 is 18 plus 2 is 20. Next step. What's the central atom? Carbon. I'll tell you now, carbon tends to always be the central atom. Hydrogen can't because hydrogen can only max out at 2. And then fluorine is more electronegative than carbon, but carbon tends to always be the central atom. So carbon will be in the middle and I will attach everything. Doesn't really matter what direction, because for a Lewis dot structure, doesn't really matter the order. But you'll have 2 chlorines and 2 hydrogens versus the way I wrote it. Don't attach those hydrogens to the chlorine, attach everything to the central atom. Okay, now I'm going to add those lone pairs to the chlorines. Always start there versus the central atom. So let's count 2, 4. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay. All my valence electrons are there. Let's make sure everything is happy. Is this hydrogen happy? Is this hydrogen happy? Is this chlorine happy? Is this chlorine happy? Okay. Is the carbon happy? Yes. So this is the correct Lewis dot structure. So look here. I can change this up into 3 hydrogen and 1 fluorine. I can change it up into, 2 fluorine, 2 chlorine, 3 hydrogen, 1 iodine. It doesn't matter. Same concept. Don't get tricked if I don't do CH4 or CF4. Like, it doesn't have to be. I can do differences here, but you still have the goods. The next step, how many things are attached to the carbon? Okay. So what is the electron geometry? What is the molecular geometry? Tetrahedral. What is the hybridization? sp3. All right, now I need to get some lone pairs involved. Let me see if I want to do a polyatomic, and then I'll do some lone pairs. Yeah, actually, let's do the polyatomic last. It's a little bit more difficult. Let's do some lone pairs. Let's do H2S. What's the Lewis dot structure? How many valence electrons? 8. So that's going to be 2 times 1 plus 6 equals 8 valence electrons. So this one, what is our central atom? I know I didn't write it the nicest. What is a central atom? Yes, it cannot be hydrogen, so it has to be sulfur. Because hydrogen can only max out at 2 electrons.
Oh, okay.
So like I can't put this here, like let's say I was to do here like this and this. This cannot be the central atom because hydrogen cannot have more than 2 electrons. Okay, so that's 2, 4, but I need to have 2 more because I'm missing 4 valence, and the only place I can put it is around the sulfur. How many things are attached to sulfur? 4. So what is the electron geometry? What is the molecular geometry? So I drew it linear, but if I was to draw it the way that you saw it on the screen, when I was doing, if I was to draw it kind of similar to what we had on the molecule, it wouldn't be linear. So don't, if you do, make sure like you don't get tripped up by that, because those lone pairs will push the other 2 away to fill up the rest of the space. So this would not be linear. It would be bent. And then lastly, what is the hybridization? It's 4 things around it, so it would be sp3. All right, I want to do one more. Let's do a polyatomic. I know that we've already done polyatomics. I don't know if I want to do harder ones. Because we could just do like NO3 again. I mean, we could also do like SO3. Do like SO3. No. Sorry, I'm like, let's do NO3. NO2. Let's do NO2 minus. It's just like you shouldn't do this unless you're 100% sure of something. But let's figure this out together. NO2 minus. All right. This is a polyatomic ion. First, we need to do the Lewis dot structure. So what are the valence here? So N, oxygen. What about this? If there's a negative sign, you add them. If it's a positive sign, you remove them. So if we did NH4, which we can do that one next, it'll be a different one. So let's do NH4 next. I have plenty of time. Okay. So 5 plus 12 is 17 plus 1 is 18. What is the central atom? Nitrogen. So that's 18. Should be 16. I'm missing. Okay. Is it happy? What's not happy? The nitrogen's not happy. So I need to, I'm adding it to the wrong place, sorry. I need to add it to the bond, make a double bond. And I'm gonna do a red one here. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, nitrogen is happy. Oxygen is happy. Oxygen is happy. This is correct. But can I make another version of this? Is it possible for this oxygen to have a double bond? And this oxygen have a single bond? Yes, so this is an example of a resonance structure because there's more than one options. Remember that you have to put in brackets and put that negative sign. And for a resonance structure, you do, this one can only have two. So it could be like this. So that's how you would draw the Lewis dot structure of something that could have more than one, and typically it's only polyatomic ions. How many things are attached to 3? So molecular geometry, sorry, no, electron geometry. Molecular geometry. No, you're right, yeah. The trigonal planar molecular geometry is, look at the way I drew it. Do you see how like I kind of made our lives a little bit harder because I didn't draw it the way it would be shaped in real life? Don't let the drawing always tell you. In this case, this would be bent. So what about hybridization? sp2, yes, yeah, I almost got it too. There's 3 things, so sp2. Okay, so we're just gonna be putting everything together now. Here is how we can apply that knowledge. This is a Lewis dot structure of ibuprofen. I'm not trying to make your lives a little bit harder right now, but what I want to do is focus on all of the central atoms. So let's look at this carbon right here. How many things are attached? 4. What is the electron geometry? What is the molecule geometry? Tetrahedral. What is the hybridization? sp3. So this is how I could ask you this question where I could give you this and I can say, okay, students with test A, what is this one? Students with test B, what is this one? Student with test, like this is how I can ask this question a million ways. So right now, let's go through and talk about each of these central ones. This carbon is the exact same. Tetrahedral, sp3. This carbon, tetrahedral, sp3, because there's 4 things attached. What about this carbon? Tetrahedral, sp3. Let's focus on this carbon. How many things attached? 3. Trigonal planar. What hybridization? sp2. So all of these in this little circle thingy are sp2, 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 sp2. This one, already did that one, sp3. Let's look at this one, this carbon. I'm focusing on the carbon. How many things? 3. So what is the hybridization? sp2. Oxygen. How many things attached to it? So each of those lone pair count as 1. So that's 4. Hybridization. sp3. And I'm not going to ask you about this oxygen because it doesn't have more than 1. If it was 2 or more, I could ask you, but I'm not. So this is sp3. So this is a good way for me to ask a question that kind of ties it in. I'm not going to ask you to make a Lewis dot structure of this. I would never do that. But could you tell me what are the shapes involved here? And could you tell me the hybridization? It's great practice. And like I mentioned, I can say test A, what about this one? Test B, this, that's why I'm having the same picture for all of you because I can be lazy, but it's not so bad. Another slide. Let's keep going. This one's called theobromine. Okay. These CH3s, that's just me being lazy. But if I go back here, that CH3 is the same thing as this. So don't get tricked if I was to leave it like this. So if I said CH3, how many things attached? 4, because this bond to the nitrogen counts. So it's tetrahedral, tetrahedral, and sp3. What about this nitrogen? Yes, I'm gonna double check this nitrogen. I think it would need a lone pair, right? This one's not showing any lone pairs. Okay, this is where she's going. So this oxygen here is missing lone pairs. This oxygen here is missing lone pairs. This nitrogen, I know is missing lone pairs because the way it's written, it doesn't have a full octet. I'm gonna add a lone pair. Same here. Same here. So that's on me, not you. So this 1, 2, 3 lone. Now that we have that fixed, let's see. So this one would be 4 things attached, and it would be tetrahedral, and then what shape? Molecular shape. So it would look like a trigonal pyramidal. Perfect. So sp3. Okay. This one right here, that's a carbon. Okay. This one doesn't show that it has a hydrogen because this is a organic molecule. Sorry, I know that this is seeming so much harder than I would ever ask you because I wouldn't. But this is an example of how we would draw a line drawing for organic students because they have a lot of assumptions in here that students who have taken 2 years of chemistry could do. I'm not asking y'all. So there is a hydrogen here. So that would be 3 things attached to this carbon right here. So that would be sp2. Make sense? What about this nitrogen? How many things are attached? Trigonal planar. What is the shape? Bent. What is a hybridization? This carbon. How many things attached? 3, so sp2. sp2. This carbon. 3 things, so sp2. This nitrogen. Tricky. There's 4 things. The hydrogen counts, and the 2 bonds count, and the lone pair counts. That's 4 things. It's a trick. So it's, what is it? sp3. This carbon. 3 things, so sp2. This nitrogen. sp3. Perfect. I forgot to do NH4s. Can we do NH4 before we wrap up? Okay. So if I have NH4 plus, and I wanted to do a Lewis dot structure. First, count the valence electrons. Nitrogen is 5. Hydrogen is 1, and there are 4 of them. But what about that plus sign? What do we have to do? -1. So 5 plus 4 is 9, minus 1 is 8 valence electrons. So central atom is nitrogen. Two, 4, 6, 8. This is the Lewis dot structure for NH4 plus. But you have to put it in brackets, and you have to put the charge out top right, just like this. Okay. I know this is a lot of new stuff, but the more we do it, the better. Right now it's 1:28. That leaves 12 minutes of class time. I'm gonna stop the recording, but I highly recommend let's doing our homework. If you have time. If you don't have time, no worries. But let's take a look at our homework and get some of the harder questions out of the way. Because these could be done quite fast because they're not even doing any math, except for the valence. Not so bad.